Okay, let's talk about another type of simple harmonic motion, and that's the physical pendulum, not the simple pendulum, right? The simple pendulum is a string length L with a point mass of mass M that swings from a pivot point, and it undergoes harmonic motion. Let's talk instead about the physical pendulum, which is a more general thing. And again, this is the kind of thing that occurs in many places, many different forms in physics, and is something that we should understand. So let's take a physical pendulum. A physical pendulum is something that could be any kind of mass that pivots on a point and swings back and forth, so undergoes harmonic motion. So let's just take any kind of mass, right? I don't know, could be a car, and let's hang that car from a pivot point, right? We call the pivot point P, and disturb it from equilibrium, and let it's still going to oscillate around point P. It's going to oscillate back and forth just like the simple pendulum did, right? So this is a physical pendulum. Okay. So I know a car is an odd thing to hang up from a point and oscillate, but point is you can make it anything. So let's just make an arbitrary, some kind of arbitrary shape, and something arbitrary, like, I guess it's like I don't know, ghost, a peanut, I don't know. And let's just put an arbitrary pivot point, right? P, pivot point. And then a center of mass. Let's say that the center of mass of this object, I'm trying to imagine what this object really is. I don't know, it's a squished marshmallow. But anyway, it doesn't matter. We're just going to pin it down just at a point P in 2 or 3 dimensions. Doesn't matter. Put an axle through it to let it swing in 2 dimensions, and it would be kind of hard to figure out a way to pin it in 3 dimensions unless you could pin it from the very top, right? You have your pivot point up there, then you could just pin it from a single string and have it swing in any direction. It doesn't matter. Anyway, let's call this pivot point, and say it's going to swing in the 2D plane. So let's just go ahead and put a vertical axis and say we are just going to displace the center. So we were at center mass. Let's find the center mass. I don't know. The center mass maybe is about here. Let's just say center of mass. So in this picture we have displaced the center of mass, because where's the equilibrium position going to be? The equilibrium position is going to be when the center of mass hangs directly under P, right? So the equilibrium position. Okay, hopefully this makes some sense. The equilibrium position is when the center of mass hangs directly under P. That was supposed to be vertically under the picture on the right. And then on the left, we have displaced it from equilibrium, and we're going to let it go so that it's going to swing back and forth about that equilibrium position. It's going to swing back. Oops, this angle wasn't supposed to be here. It's going to swing back and forth about the equilibrium position. Okay, so this is our physical pendulum. Let's go ahead and analyze this physical pendulum. And we can analyze this physical pendulum using torque. What do I mean by that? Well, when we talked about the mass in the spring, in order to write down an equation of motion, we had to start with Newton's second law, F net equals ma. But here we've got rotation, so we're going to start with torque net equals I alpha. Torque net equals I alpha. And we can find the net torque about the pivot point, or the restoring torque, right? So and the net torque is going to be the restoring torque, right? Because when we pull this, so again, the picture on the right is equilibrium, and we have now the picture in the middle, we have pulled it away from equilibrium. What force is pulling it back towards equilibrium? What force is pulling it back towards equilibrium? I guess I didn't explicitly say, but the only way that this is actually going to move when I pull it away from equilibrium is if this is hanging in the Earth's gravitational field, right? So the acceleration due to gravity is still in that direction, and so what's pulling it back towards equilibrium is indeed gravity, but gravity exerts a torque to rotate it about the pivot point. right? So the net torque about the pivot point, what we need to do is we need to treat the body, right, at the center of mass and ask the gravitational force is going to be pulling down at the center of mass, so that's gravitational force. And that gravitational force, only the tangential component of that gravitational force, tangential to the rotational circle, right? So look at the center of mass. The center of mass is going to rotate along that red line. So the center of mass, is going to rotate depending on how high we, that was supposed to be red. Red. It's going to rotate, right, as if with P at the center, right? This is radius R to the center of mass, and the center of mass is going to rotate in a circle about that center point P. Now, look at the gravitational force. The gravitational force has two components. The gravitational force has a component which is parallel to the radius R, and a component which is perpendicular to the radius R, or tangential to the circle of motion, right? So the only thing that is going to move the squished marshmallow back towards equilibrium is the component of gravitational force pointing tangential to the motion. So the net torque is given by that component of force. That force is the component of Fg. Remember, the angle theta is in here. This is the angle theta. So that component of force is Fg sine theta. Now that's the force, and so the torque is R times Fg sine theta. And that is in the opposite direction of theta. Theta is our positive direction, right? We just like when we pulled out a distance x, the restoring force was in the opposite direction. Theta is counterclockwise, and that torque is clockwise. So there's going to be a minus sign here equals I alpha. I'll take away the vector sign because now we know the direction. This is a one-dimensional motion problem where it's clockwise or counterclockwise. The restoring force is in the clockwise direction, and the theta, or the direction of motion currently, we've moved it in the positive direction in order for the restoring force to be in the negative direction. We moved it in the counterclockwise direction. So then, you might be asking, alpha, what's alpha? Remember, alpha is the angular acceleration, which is the second derivative of theta. Hence, theta is in the counterclockwise direction, and torque is in the counterclockwise direction. Hence the minus sign. Again, the minus sign comes from the fact that the torque is in the opposite direction of theta. On the right-hand side, we have I d squared theta dt squared, right? The second derivative of theta. And on the left-hand side, we have what I'm going to replace Fg with the force of gravity with mg. This whole object has a mass m, right? So let's say that has a mass m. So therefore, I'm going to just replace that with minus r mg sine theta. Okay, so this here is our equation of motion. This last thing that I wrote down is our equation of motion. This is the Newton's second law equation of motion of the physical pendulum. It tells us about the relationship between its acceleration and its displacement, or angular acceleration and angular displacement. And is it simple? Is it simple harmonic motion? Think about it. What does simple harmonic motion mean? Simple harmonic motion means that the force is proportional to the displacement. I just wrote the force is proportional to the displacement. Therefore, it would mean that the torque is proportional to the angle. The equivalent, right? If everything in linear motion has an equivalent in rotational motion, that should be set in your mind, right? That everything has an equivalent. So if simple harmonic motion means force must be proportional to the distance from equilibrium, it also means that the rotational equivalent of force must be proportional to the rotational equivalent of distance from equilibrium. So that means torque must be proportional to theta. So the torque must be proportional to theta in order for it to be simple. Is the torque proportional to theta? I'm waiting for you to answer. No, it is not proportional to theta. What is the torque proportional to? Look at the torque, right? The torque was this equation right here. The torque is here, the torque is here, the torque is here. The torque is proportional to sine theta, which is not proportional to theta, right? Theta, as I pull the object away from equilibrium, as I pull it up in the counterclockwise direction, theta gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, depending on how far I pull it. Just keeps getting bigger. Theta goes from 0 to 1 degree to 2 degrees to 5 degrees to 15 degrees to 150 degrees to whatever. What does sine theta do? Sine theta gets bigger and then smaller and then bigger and then smaller and then bigger and then smaller. So they're not the same thing. But we can use what's called the small angle approximation. Minus RMG sine theta is equal to I d squared theta dt squared is not simple harmonic motion. It's harmonic motion. It's not simple. But if we say if theta is much less, if not much less than, if theta is small, then we know, and you have probably seen this in math before, sine theta is approximately equal to theta. Sine theta is approximately equal to. Sine theta is approximately equal to theta. It's called the small angle approximation. Small angle approximation. And you might ask, what does it mean for it to be small? It depends on how accurate we want to be, right? That's just like the approximations that we use in relativity. It depends on how accurate you want to be. In this case, the approximation isn't so exact as in relativity. And we actually will study this in advanced lab when we do the harmonic motion lab in advanced lab. What does small mean? But in general, you could go ahead and put numbers into your calculator. And by the way, in order for this to work out on your calculator, you've got to use theta in radians. Sine theta is approximately equal to theta for theta in radians. Put it in your calculator. Put your calculator into radians and put in 1 radian, 0.1 radians, 0.1 radians, right? 0.1 radians, you'll find that the sine of 0.1 radians, so let me just do it. So I just put this into my calculator, and indeed, it is correct within, what is that, 0.1%, I think, 0.1%. And 0.1 radians, remember 0.1 radians, you should know this, but 0.1 radians is about 6 degrees. So it seems pretty accurate for about 6 degrees. And typically, we figure the small angle approximation gives us pretty good results, depending on how accurate we want to be, but right within less than a percentish if we're at, if we're under 10 to 15 degrees. So theta less than less than approximately equal to 10 or 15 degrees, right? 10 degrees. Small angle approximation works. Okay, so if we use the small angle approximation, therefore we can approximate this equation. RMG sine theta is approximately equal to theta. RMG theta equals I d squared theta dt squared. Is this simple harmonic motion? Yes, this is an equation of simple harmonic motion because this shows that the torque is the net torque is proportional to theta. And this shows that it's harmonic because the restoring torque is in the opposite direction of theta, of the acceleration. Whatever. Theta is in the opposite direction of the acceleration. Theta is in the opposite direction of the acceleration. Okay. So now, what is the solution to this equation? Well, that is not a difficult thing to do at this point. It might look weird. It might look like something where you're a little bit thrown off. I don't know what this equation means. Well, let's first of all make sure we understand what this equation means. Let's just take our arbitrary object, squished marshmallow. I just changed the shape. Here's our center of mass. There's our P. We've displaced it from equilibrium by some angle theta. This object has a mass m. R is where we put the pivot point, right? That's where we're going to pivot it. So R is the distance to the pivot point. Here, let me put P up here. R is the distance to the pivot point. I, what is I? Wait, G is the acceleration due to gravity. And the only thing left is I, right? Everything else is shown in the picture. What is I? Do you remember? I is the moment of inertia. I is the moment of inertia. And the moment of inertia is equal to some number, right? I'll just call it constant c times mr squared. That is the moment of inertia of the object. A point mass at a distance r from the pivot point, if it was a point mass, that has a moment of inertia of mr squared, right? Remember that? And so more complicated objects have some different moment of inertia. But I'm not going to review moment of inertia. You should go back to rotational motion and review that for yourself if you don't know what it is.